Okay, so the first thing, maybe you saw this on D2L, but on Thursday, we're going to do the first quiz. We should have had a couple by now, so now we're going to get going. I'm the department chair this semester, and I've had a lot of stupid administrative stuff, but I know I owe you some grading and stuff. I'm going to get to that now, so we'll get everything, the ship righted, you know. So quiz 1. Is on Thursday. And the quizzes, this is listed in the syllabus if you want to read in detail about what the quizzes are compared to the tests. The tests, the exams, are all problem solving, you know, doing things like the homework problems. The quizzes are just short answer questions about the lecture, you know. And so it's my way of getting you to read your notes, you know, go back and skim through your notes, read through your notes. So there's not going to be any calculations. I'm going to try to focus on what I consider to be the big things. You know, I'm not going to try to grill you on like what I consider to be like really like minutia or anything. But so to get ready for the quiz, just go back to the beginning of your notes and just read through and try to make a mental note of the things that are important. For the first one or two, there's a good chance, like it's sort of a figuring out process, like what kind of stuff I'm going to ask about, and I don't really have anything more to say about that, I think. But I do drop the 2 lowest quiz scores, so if you study totally the wrong stuff, you know, that just is one of the quizzes that gets thrown out. It's not that big a deal, you know. But before Thursday, you want to go back to your notes, read back through it, remind yourself about the big ideas, definitions, stuff that says notice, you know. There are places in the notes where I have a little star and it says notice. Those are things that I put on there a lot, okay? Anybody have any questions about the quiz? It's going to be 5 or 10 minutes right at the end of class next on Thursday. Okay. Anybody have any homework questions you'd like me to go over? All right. So here's what we've been doing. So we did Newton's second law, and then we started talking about kind of special cases. So let's call it special cases for Newton's second law. These are just different configurations that, you know, different connections of bodies and stuff like that sort of ask for their own way of solving things. They're all things like, you know, you could figure out just from Newton's second law, but I think it's helpful to just talk about specifically how to deal with these cases. The first one was connected bodies with the same acceleration. Okay, so that was the one where we said first you isolate the whole system, calculate the acceleration, then go to the individual bodies to calculate forces and stuff. So we're done with that one. The next one we're going to talk about, the one we're going to do today, is rolling and sliding problems on inclined surfaces. Well, we've already done rolling and sliding problems on horizontal surfaces, but what if you're on like a ramp, you know? So this will tell you how to approach just generally the same kind of problems we've done, but when you have a tilted surface. And then the last one we're going to do, which will be on Thursday, is So connected bodies with different accelerations and this happens when pulleys are involved. So two bodies that are connected by a cable and the cable goes over a pulley. That changes the motions of the two things because the pulley changes the direction of that the cable is lying. And so we'll talk about that on Thursday. Okay. When we, excuse me, when we talked about vectors, we talked about how the same vector could have different components in different coordinate systems and how to come up with the components in different coordinate systems. And you were like, this is stupid. Why do we have to do this? I'm never going to do this. But now you're going to see why. So let me just remind you, I mean, you might not have sounded that mad when you said it, but I know inside your head, that's what you were thinking. Okay, so if you have a coordinate system, well, sorry. So let's say we have a vector like this, okay? And let's say that it has a magnitude of 100. Okay. And we want to calculate the components in a coordinate system like this, bless you, and then a coordinate system like this. Where this angle is 20 degrees. Okay? You remember doing problems like this in the vector assignments, right? Okay, so for the first one, for A, really the procedure for all of them is take the tail of the vector, put it at the origin, and then determine the coordinates of the head of the vector. Okay, so this vector has a length of 100. That's in the negative y direction, so the components of this vector would be 0, negative 100. And then what about that coordinate system at B? So now we have a coordinate system like this, where the x-axis is 20 degrees from the horizontal, like that. Put the tail of the vector at the origin. Okay, and we're trying to, again, just calculate the coordinates there. Okay. Well, what's the angle from the vector to the negative y-axis? Can you picture that? I think it's easiest to imagine if you think of starting with the coordinate system straight and then tip the whole thing 20 degrees, you know? Then that's going to go down 20 degrees from the horizontal. And this is going to go out 20 degrees from the vector. Can you picture that? Anybody want to clarify anything? You have any questions about that? Okay, so what that means is that this angle is also 20 degrees. Okay? And that negative y-axis here is since we always measure our angle for cosine and sine from the positive x-axis, the negative y-axis would be 90, 180, 270. Okay? So what is the angle to get from the positive x-axis to this vector? 290. Yeah, 290. Do you see that? Because you would get to the 270 line and then go 20 more degrees counterclockwise. Okay? And so the components of this vector would be 100 times cosine of 290, 100 sine of 290. And that is 34.2 negative 94.0. Okay? So you did exercises like that. It wasn't clear yet what we were going to use it for. But now here's what we're going to use it for. For rolling and sliding problems, choose a coordinate system, CS, coordinate system, with the y-axis pointing straight out of the surface, and that means that the x-axis is along the surface. So if you have an incline like this, where this is 20 degrees, and you have an object rolling along that surface or sliding along it, the coordinate system we're going to use has the y-axis pointing straight out and the x-axis along the surface. Okay? Well, notice that for this incline, that coordinate system that we're going to use is this coordinate system here. Okay? And so we're going to have to re-express all our vectors in this coordinate system. Okay? Is there a reason that you would have to rotate the coordinate system? No, you can always do any calculation in any coordinate system you want. The reason we're going to do this is because it makes a lot of things easier. Okay? It makes one thing harder, though, unfortunately. So let's think about what we benefit, what the benefits are and what the drawbacks are. Okay, so the first benefit, think about the acceleration of the object. So if this cart is rolling along that incline, and we used a regular coordinate system like this, the acceleration of that cart would have an x component and a y component. You see that? It wouldn't just be moving along a horizontal x-axis like we're used to, or a y-axis like we're used to. It would be rolling a little bit in the positive x and a little bit in the negative y, or the opposite of that, But so the first benefit of using a rotated coordinate system like this is that the acceleration vector stays simple. The acceleration vector we're always just going to represent as a0. Okay? Since we always put the x-axis along the surface, the thing is always going to be moving along the x-axis. Okay? So that's one place that we don't have to use cosine and sine, and that's nice, The second benefit is the normal force. So when you have things that are rolling or sliding, the surface is always pushing on the object, okay? So that's the normal force. That's the pushing force that I usually call N. And the components of the normal force, the pushing force from the ground, since y is pointing out of the surface, this is always just going to be 0 n. One thing about, go back to the acceleration for a second. Notice that we don't know, until we do the calculation, we don't know which direction this thing's going to accelerate. So the answer could be plus or minus. But we'll write it as A0. The normal force we actually know is always going to be positive because the pushing force is always toward the body. And then the last thing is the friction force. That's always opposite the direction of the velocity, opposite the direction of motion. And so it's going to be along the x-axis, and that's going to be always either plus or minus whatever the coefficient of friction is, times the normal force, and then 0 for y. Okay? So all three of these vectors, if we used a non-rotated coordinate system, the one we're used to using, we would have cosines and sines everywhere on all of these. And that would be a pain, you know? There's one thing that gets more complicated, though. So there's only one drawback, and that's why this is always going to be worth doing. You know, you get 3 benefits and only one drawback. But the drawback is the weight force vector. That weight force vector used to always just be along our negative y-axis. And so we always wrote it the same, 0, negative, whatever the weight is, you know? But now we're going to have cosines and sines show up in our weight force. And that's sort of what I did here. If you think of that 100 Newton force as the weight of an object, okay? In our old coordinate system, that just showed up as 0, negative 100, okay? But now, with this rotated coordinate system, it would show up as the weight times a cosine and a sine thing, okay? And so the weight now is going to be mg times the cosine of some angle, mg times the sine of some angle. And that angle theta is always going to be if phi, so that's just another variable that you use for angles a lot of times. If phi is the angle of the incline from the horizontal, then this angle theta is going to be 270 plus or minus phi. And you'll have to think about whether it's plus or minus. That'll depend on the way the ramp is going. We'll get to problems like that. Okay, so let's go back again to this example. So if this is the weight force, 100 newtons, and we're using this coordinate system that's tilted 20 degrees from horizontal. You can see that in this picture. Okay. Then in this case, to get from the x-axis to the vector, we had to go cosine and sine of 270 plus 20. Okay. If that was tipped 20 degrees the other way, that way, then the 270 line would be over here, and we'd have to do 270 minus 20 degrees. Anyone have any questions about that? Okay, well, let's just get into, do some problems, and we'll sort of see how it works. But just remember that all we're doing, we're going to draw the free body diagram just the same, and just like always every other time, the free body diagram gives you all the force vectors that show up in Newton's second law, okay? It's just that those vectors are expressed in a different coordinate system now. Okay, so let's start with I'll start with one at the angle that I showed so far. So let's say the ramp is at 20 degrees like this. And there's the mass. Let's say that it has a mass of 10 kilograms. And we want to calculate the acceleration vector. Well, to make our lives easier, believe it or not, we're going to choose a coordinate system with the y-axis out of the surface, the x-axis along the surface, like that. A free body diagram. Now, the free body diagram isn't any different than it was before because it just shows the vectors as arrows. It doesn't have to do with components. So, okay, what does the free body diagram look like? There's a weight force that's straight down. That's 10 times 9.81. And then the only other place the surroundings contact the boundary is the pushing force from the ground on the wheels. So that's perpendicular to the surface toward the body. And you can see in that picture that since this is at an incline, that weight force and that pushing force from the incline are not parallel to each other, okay? They're like 20 degrees apart because of the incline. That's all the forces. So now we can go to Newton's second law. Before I do that, no, not before. So Newton's second law. Let's put all this stuff in. Okay, so there are two forces. The pushing force from the ground, that's the normal force. That's the one that's always just going to show up as 0n. Because notice it's just acting straight along our positive y direction, so 0n. And now we have to deal with that weight force. Well, our coordinate system is this. This is our 270-degree line. The weight force is this. That has a magnitude of 98.1. This angle is 20 degrees. And so to get from the positive x-axis to the weight force vector, you have to go 290 degrees. So this is going to be 98.1 times the cosine of 290. 98.1 times the sine of 290. Put everything in as positive, and the sine and cosine will do the plus minus signs for you, you know. So you get 33.55, I think, for x. And then, let me punch this in. Negative 92.18 for y. So this gives you the components of the weight force in Newton's second law. Those are the only two forces, so this is equal to the mass, 10 kilograms, times the acceleration, which is always just going to show up as a0. Okay, so now Newton's second law gives us two equations. The x equation from Newton's second law says 0 plus 33.55 is equal to 10a. And the y equation says n minus 92.18 is equal to 10 times 0, so 0. We're trying to calculate the acceleration vector, which is this. You know, we already almost have it. We just need to know what that variable a is so we can plug it in there. Okay, so which equation do we want to calculate that variable a? The x equation or the y equation? X, yep. So we're going to take this one. You know, there's nothing wrong with the y equation. It just doesn't give us what I asked for, you know. If I was asking what the force is that the surface applies to the cart, then we would want the y equation. But in this case, we want the acceleration. So this one says 33.55 is equal to 10a. And so a is equal to this divided by 10, which is 3.36 meters per second squared. We want the acceleration vector, so plug this back now into the vector, this, to get the, and you get that the acceleration vector is 3.36 for x, 0 for y, meters per second squared. Or if you want to visualize the direction of it, it's in the direction of our positive x-axis, which is down the ramp. With a magnitude of 3.36 meters per second squared. Any questions about that? Okay, let's do another one. Similar thing. So this time, let's say that the ramp is like this. And this is a 30-degree angle. Let's say the mass is 5 kilograms. And let's say that there's some force, we don't know what it is, but it's pushing this thing, trying to push this thing up the ramp. Let's say that it has a magnitude of 10 newtons. So let's calculate first the force vector applied to the cart by the surface. And second, let's calculate the acceleration vector. And the coordinate system we're going to use has the y-axis pointing straight out of the surface and the x-axis along the surface. So start with a free body diagram. There's a weight force acting straight down. That's 5 times 9.81, so 49.05. There's this 10 Newton force that's applied over here. And then there's the pushing contact on the wheels from the incline. And so now we can go to Newton's second law. The 10 Newton force is exactly in the positive x direction, so that's just going to be 10, 0. The normal force, like always, is just going to be 0, n. We have to calculate the weight force. I'll do that in a second. And then these are going to be equal to the mass times the acceleration vector, which is always just this. Okay, so now let's calculate that weight force vector. The coordinate system is this. The weight force is this, 49.05. And this angle here is 30 degrees. Okay, so take a second and see if you can figure out what the angle is for the cosine and sine going from the positive x-axis to that weight force vector. So we're just trying to figure out that angle theta. Okay, what angle do you think that is? 240, that's right. So this time you go from the positive x-axis, you go, here's 90, 180. It would be 270 if we made it all the way to this, but we fall 40 degrees short of that. So it's 270 minus 40, you fall 30 degrees short of that. So it's 270 minus 30. So this angle is 240 degrees. The reason we subtracted from 270 instead of adding is because of the angle. You know, it's like, is that incline rotating clockwise or counterclockwise from the regular coordinate system? Anybody have any questions about that? Okay, so now this weight force vector is going to be 49.05 times cosine and sine of 240. So that's going to be negative 24.525. And can someone calculate 49.05 times sine of 240?
Negative 42.47.
What is it?
Negative 42.47.
Okay, thank you. So like that. Okay, so this gives two equations. It always gives two equations. The x equation says 10 plus 0 minus 24.525 is equal to 5a. And the y equation says 0 plus n minus 42.47 is equal to 5 times 0, so 0. We're asked to solve for two things. We're asked first to solve for the force vector applied to the cart by the surface. Well, that's this one. So all we need for A is to calculate N. So we want the y equation for that to calculate N. So you get N minus 42.47 is equal to 0. N, add 42.47 to both sides. You get N is equal to 42.47 newtons. Now plug that into this force vector, and you get that the force vector on the cart by the surface is equal to 0.42.47. That's in the positive y direction, so if you want to visualize the direction, that's this way with a magnitude of 42.47. And that kind of calculation is really important for engineering applications, because a lot of times you're trying to figure out how strong you have to make something so it won't break, without spending a ton of extra money on, you don't want to make that ramp out of titanium if you can make it out of plastic, that kind of thing. And so what we know from this calculation is that ramp and those wheels have to be strong enough to withstand this force of 42.5 newtons. Any questions about that part? Okay, and then for part B, now we're trying to figure out the acceleration vector. So that's this. And so for that one, we're going to use the x equation. So the x equation says 10 minus 24.525 is equal to 5a. So you get negative 14.525 525 negative is equal to 5a. Divide both sides by 5. And you get a is equal to 2.905 meters per second squared. Plug that into the vector, and you get an acceleration vector of 2.9. Oh, I left off the negative, sorry. It's negative. So you get an acceleration of negative 2.905 for x, 0 for y. And if you want to visualize that, it's in the negative x direction. So that way, with a magnitude of 2.905 meters per second squared. Any questions about that? Okay. So that's for rolling problems. Let's do a sliding problem now with friction. So let's say we have an incline like this. The angle is 25 degrees. This has a mass of 0.5 kilograms. At the instant shown, remember for friction problems, you always have to know which direction the thing is sliding because friction is always opposite that. So let's say that at this instant, the box is sliding up the ramp. That would be like if someone had just given it a big shove, and so it's still sliding, but that the force that caused that slide is gone, you know? And let's say that the coefficient of friction between the block and the ramp is 0.2. So let's say we want to calculate the friction force vector. And second, the acceleration vector. We're going to use this coordinate system. So start with a free body diagram. You have a weight force straight down. 0.5 times 9.81 is 4.905 newtons. And then you have a friction contact with the surface, and that's made up of two things. A pushing force, I'll call that N. And then a friction force that's opposite the direction of motion. So the friction, you know, since it's sliding at this instant up the ramp, the friction force is down the ramp. And the magnitude of that is the coefficient times the pushing force, the normal force. And there's nowhere else that the surroundings contact the boundary, so we know we're done. And so now we just have to represent all this in Newton's second law. There's the pushing force, 0N. That always appears the same way. The friction force is always in the positive or negative x direction, but we have to think about whether it's positive or negative. In this case, it's in the direction of positive x. So I'm going to put that in as 0.2 times n, and then 0 for y. Then we have the weight force. So let's think about the weight force. There's x, there's y. Here is the 270-degree line. The weight force is this. This angle here is 25 degrees. And so what's the angle theta that we need to use here?
295.
295. Yep. So if you start at x, you go around, you hit 270, and then you have to go 25 more degrees. And so the weight is going to be 4.905 times the cosine and sine of 295. Yeah. So for the x component, that's positive 2.07. And for y, it's negative 4.45. And then all these forces are equal to the mass times the acceleration. To solve these problems, so for the rolling problems, you can always just choose which equation works for what you're trying to solve. For the friction problems, you're always going to start by calculating n using the y equation, and then you're going to plug that into x to solve whatever you're looking for. Okay, so for friction, you're always going to go y equation to calculate n, and then you're going to plug n into the x equation. So that y equation says n plus 0 minus 4.45 is equal to 0.5 times 0. Add 4.45 to both sides, and you get that n is equal to 4.45 newtons. Then plug that into the x equation. So the x equation says 0 plus 0.2 times n, which now we know is 4.45. Plus 2.07 is equal to 0.5a. The friction force is this. So now that we know n, we can say what that is. And the acceleration vector is this. So we just have to calculate a for that. So for part A, the friction force, I'll write it like that, force of friction is 0.2 times 4.450. And that is 0.890. And that's in newtons. So in other words, if you want to visualize that, the friction force is in the positive x direction down the ramp with a magnitude of 0.89 newtons. And then for B, we just have to calculate that variable A. So we have 0 plus 0.89 plus 2.07 is equal to 0.5A. So 2.96 is equal to 0.5A. And so A is equal to 5.92 meters per second squared. And so the acceleration vector, just plug that into the acceleration vector in Newton's second law up here. 5.92 for x, 0 for y, or in other words, positive x direction with a magnitude of 5.92 meters per second squared. Okay, and then the last question for interpreting this is, well, in these kind of problems, we always have to be given the direction of the velocity to do the problem. So is this block speeding up or slowing down? And how do you know?
Slowing down.
Slowing down because the velocity is up the ramp, and we figured out that the acceleration is down the ramp. And so if they're opposite each other, then it's slowing down. Okay? Any questions about that? Okay, so this approach to rolling and sliding problems, you can use it with collections of bodies like we've already done. Let's do one like that. So let's say that you have a ramp that's at an angle of 10 degrees. And let's say there are two carts that are connected by a cable. Let's say this is 1 kilogram and this is 2 kilograms. And let's say that, hold on a second. So let's say we have this force F, and we're going to calculate two things here. So first, if F is 10 newtons, what's the force, let me reword this. What's the tension in the cable that connects those two? And then second, what does F have to be so that the acceleration is 0 for this system? Okay, so first we're going to assume that that's 10 newtons. So how would we go about calculating the tension in the cable? We're going to do it the same way that we did problems like this when it was horizontal. We'd first isolate the whole system as a thing to calculate the acceleration, and then we'd go back and isolate an individual thing. Okay? So for the first thing, so we'll start with a free body diagram of the whole contraption. We have a weight force down. What's the mass of the whole thing? 3. So 3 times 9.81 is 29.43 newtons. And then that force F, for now we're assuming that that's 10 newtons, so I'll put that there. And then we have a pushing force from the ground that I'll call N total. And this is at an angle compared to the weight force. We're going to use this rotated coordinate system. So Newton's second law says we have 10 in the positive x direction, N total in the positive y direction. The angle for that weight force is going to be 10 degrees short of 270. So this is going to be 29.43 times cosine of 260, sine of 260. And all that is equal to the combined mass times the acceleration of a0. So this, if you multiply this out, you get negative 5.11, negative 28.98. The x equation says 10 plus 0 minus 5.11 is equal to 3a. So 4.89 is equal to 3a. So a is equal to positive 1.63. And so that tells us the acceleration vector of this system is 1.630. And now we want to calculate the cable tension between the two carts. So we can isolate either one of these to do that. We'll get the same answer either way. I guess I'll isolate the 1 kilogram. So we have the weight force of 1 times 9.81. A pushing force, I'll call that N1. The only other place where there's contact with the boundary of the 1 kilogram is that cable. So we have a pulling force this way, and I'll call that T. And Newton's second law says 0 N1 plus T0 plus 9.81 times, this angle stays the same because it's still the same ramp. So 9.81 times cosine of 260 sine of 260. And if you multiply this out, you get negative 1.70, negative 9.66. And then this is all equal to the mass, 1 kilogram, times the acceleration vector, 1.630. The x equation says 0 plus t minus 1.70 is equal to 1.63. So t is equal to positive 3.33 newtons. And then if you wanted the force vector instead of just the tension, you could plug it into a force vector to get what direction it is. But if it just asks for the tension, then you can just give it as a number. Just that number is fine. Okay. Anybody have any questions about that part? Okay, so then the question is, last thing. So the question is, what would this F have to be so the acceleration is 0? What would be happening with this system if that acceleration is 0? This is a trick question. So you're probably going to be wrong. I'm probably going to make fun of you to my wife later. Hey, it's our anniversary today, 19 years. 3 more to go.
Yeah.
Just kidding. Okay. So what's going to be happening if the acceleration is 0? It could be not moving, but that doesn't have to be the case. It also could be moving with a constant velocity. Okay? So, so it could be moving with a constant velocity down the ramp or up the ramp, or it could be stopped. We don't know that. With the friction problems, I always have to tell you which way it's moving. So it's kind of like in your head, it could be, you understand that it's moving. I tell you what way it's moving. With this, I don't tell you which way it's moving because the answer for acceleration and forces are going to be the same no matter which way it's moving. You know what I mean? But remember that 0 acceleration just means the velocity is constant. And the answers we're going to get for part B could have it moving with a constant velocity down the ramp or up the ramp, or it could be stopped. Okay, so for part B, so let's isolate the whole thing again. We have a weight force down of 29.43. We have a pushing force from the ramp of N total. We have a force here that we don't know, and that's it. So Newton's second law says 0 N total plus the weight, which we know is just the same. We're still using the same coordinate system we used in part A, so this weight is going to be the same as in part A. So that was negative 5.11, negative 28.98, negative 5.11, negative 28.98. And then that F is in the positive x direction, so this is F0. And all that is equal to the mass of the system times the acceleration, which now we're specifying is 0. So we have an x equation that says 0 minus 5.11 plus F is equal to 3 times 0. And so that force F would be 5.11 newtons. Any questions about that? Okay, well that's it for today. So be ready for quiz at the end of class on Thursday. And we'll get into next time the last one of these things, which is going to be connected bodies with different accelerations.